This video is supported by the National Science Foundation.
Hi, my name is David Selassie Kobler, and I'll be walking you through the various imaging modalities you will need to understand hardware security, especially for reverse engineering. In this module, we will discuss what an image is and try to understand its components. Once we understand what an image is, we will look at the various imaging modalities available. We will look at optical imaging, we'll discuss X-ray imaging, we'll delve into terahertz imaging, and finally conclude with scanning electron microscopy. So with that in mind, let's begin our lesson. Let's dive right into the understanding of a digital image. At its core, a digital image is just made up of pixels, which are the fundamental building blocks of an image. The picture elements or pixels are just number representations of intensity, which define color or gray level depending on the type of image. The pixel is just an output of a two-dimensional function operating along the x and y axes. So in a visual representation, you will see a grid of pixels, each assigned specific numerical values. The arrangement is formed as you can see on the xy plane, and these interplay together to form the visual content that we can see. A black and white image can be seen to have only specific levels of gray. But for a color image, you will realize that each channel, which you may be familiar with as the RGB or red, blue, green mode, has specific intensities assigned to it. The intensities assigned for each red, blue, and green channel combine as individual 2D grids to create a color image. Now that we know digital images and what they are composed of, let's move on to optical imaging. Optical imaging is the imaging method we are very much familiar with. Optical images are simply pictures created by lens or a system of lenses, and they can be created by reflections, refractions, or diffractions. These images usually capture scenes from nature and are the most common ones that we get. Now think about the devices you have for optical imaging. You may have your iPhone or a DSLR camera. Or maybe if you are older than a specific age I don't want to mention, you may have access to a film camera. Most likely you'll have a camera phone. These days they are very common, but they weren't 15 years ago. We can see that technology has played a part in the development of optical imaging, and even now, for hardware security, specifically hardware reverse engineering, we are able to use smartphones to capture certain aspects that we can use to create an understanding of the device under test. Now that we know optical imaging, let's dive into another one that we may be more familiar with. Now let's talk about X-ray imaging. You may be familiar with X-ray imaging if you have had broken bones or a chest infection. X-ray imaging relies on electrons being emitted. It's very non-destructive and really plays a crucial role in volumetric analysis of a living body or an object. Some of the common forms of X-ray imaging include radiography, which produces a two-dimensional image, and computed tomography, which is actually the preferred method in hardware reverse engineering. Computed tomography, or CT, generates a three-dimensional representation by compiling several two-dimensional projections, and this gives a very comprehensive view of an object's internal composition. In medical settings, there's also fluoroscopy. This technique provides real-time dynamic images of organs and allows for continuous monitoring during medical procedures. X-rays are very versatile and they have applications well beyond medicine and even electronics. X-ray imaging is still used today and is a very valuable tool in many forms of industry. You would be very surprised where X-ray imaging is used throughout our world. Now that we know X-ray imaging, let's look into another form of imaging. Terahertz imaging is a non-destructive evaluation technique which uses terahertz frequency range to assess objects. Terahertz generally falls between microwave and infrared, and it allows for the retrieval of information about electric and non-conductive materials. It has really diverse applications, especially in assessing the properties of materials without altering their structure. Unlike other imaging methods, it can actually penetrate non-metallic materials and provide detailed information about their composition. One interesting part of terahertz imaging is its similarity to thermal imaging. In fact, this is clear using the image that we see on the right, where heat signatures can be detected and analyzed. In terahertz, the focus is actually capturing information about the electromagnetic properties of materials. It has so many interesting applications, especially in pharmaceuticals and security screening. It has the potential to even unveil hidden details of objects without any non-invasiveness. Although it's not widely known, it is very common in the hardware security community and has gained traction as a method of understanding electronics and assuring their validity and functionality during usage. Now let's get into our main imaging procedure. Let's discuss scanning electron microscopy. Scanning electron microscopy is actually the most relevant imaging modality you will need for your lessons throughout these modules. Unlike optical microscopes that use light, scanning electron microscopes, or SEMs, use beams of electrons that give them a wide range of depth of field. You will understand more about this in the next lesson. The SEM, or scanning electron microscope, uses a focused beam of high energy electrons to generate different signals at the surface of the solid specimen. In our case, our specimen would be the IC. The signals that we derive from the interactions between the electrons and the samples reveal information about the sample's texture, its chemical composition, its structure, and even its orientation. The data collected over a selected area of the surface of the sample is a two-dimensional image, which can produce a three-dimensional rendering of the object itself. Areas ranging from almost 1 centimeter to 5 microns in width can be imaged using the SEM. It also has magnification ranging from 20 times to over 30,000 times as well as spatial resolution, which is important for distance, of 50 to 100 nanometers. The SEM can actually perform pinpoint analysis of specific locations or points of a sample. And this is very important when one wants to do chemical analysis of the composition of a device. In our case, we would know what ICs are mostly made of, since we learned that in our last lesson. The SEM overall is very renowned for its impressive resolution and its ability to resolve nanometer scale distances. You can see even in the images that are provided that you can actually notice the three-dimensional depressions on the surface of the device. You will find that SEMs are very handy in hardware reverse engineering and have made giant strides in allowing us to really analyze and replicate some of the devices based on our various needs. Now that we know a bit about SEM imaging and we have examples, let's move on to how SEM imaging works. Here is an image of the scanning electron microscope. This is a generic version because there may be different configurations available, and technology continues to improve the operations of the current setting. This is the most generic version, and you would find in it the electron gun, which emits electron beams, an anode, magnetic lens, the scanning coils, the various detectors for the various types of signals emitted, and then a stage for the specimen under test. You also notice that it has detectors surrounding it to pick up these signals and form an image that the user can understand. So you would ask, how exactly is the imaging process enacted? Well, it starts with the emission of the beam of electrons, as you can clearly see in the image. Once you have a beam of electrons being produced, they travel through an electromagnetic field, and the lenses you see, specifically the magnetic lens, focuses this beam towards the sample on the stage. Once the beam hits the sample, the electrons and rays are ejected from the sample. The rays being X-rays and the electrons being emitted as they interact with the sample. The detectors collect these X-rays and the emitted electrons and then secondary electrons and converts them into a specific signal. This collected signal is picked up and converted into an image that you'll be able to see on their fixed screen. You don't really see the screen on the image we have in the slide, but a conventional SEM would have, for example, a computer screen that a user can refer to and follow the entire structure of the device under test. This is how SEM is performed on a sample. Remember that the samples we are speaking about are ICs or integrated circuits. Now that we know and understand SEM imaging and we have a good understanding of ICs or integrated circuits, let's combine this knowledge and move on to our next set of lessons on hardware reverse engineering.